Have you ever looked up at the night sky and wondered what's lurking in the darkness between the stars? What if I told you there are monsters out there, so massive they defy comprehension, so powerful they swallow light itself? These are supermassive black holes, and today we're diving deep into the evidence that proves these cosmic behemoths are very, very real. If you love exploring the biggest mysteries of the universe, hit that subscribe button, like this video, and ring the notification bell so you never miss an adventure. All right, let's get into it. For a long time, supermassive black holes were just a wild theoretical idea. I mean, an object with the mass of millions, or even billions, of suns, all crushed into a space smaller than our solar system. It sounds like science fiction. But over the last few decades, the evidence has been piling up, turning this sci-fi concept into a concrete astronomical fact. And it all starts with watching the stars. One of the most compelling pieces of evidence comes from the very center of our own galaxy, the Milky Way. At its heart lies a region called Sagittarius A. For years, astronomers have been meticulously tracking the orbits of the stars closest to this central point. Imagine trying to follow a tiny speck of light for decades, mapping its path with incredible precision. That's what teams of astronomers, like those led by Nobel laureates Reinhard Genzel and Andrea Ghez, have been doing. What they found was absolutely mind-blowing. These stars are whipping around a central, invisible point at incredible speeds. One star, named S2, completes its orbit in just 16 years, reaching speeds of over 25 million kilometers per hour as it swoops by this unseen object. Think about that. Planets in our solar system take much longer to orbit the Sun, and they're much closer. For S2 to be moving that fast, it has to be orbiting something with an immense gravitational pull. By applying Kepler's laws of planetary motion, the same laws we use to understand our own solar system, astronomers could calculate the mass of the object these stars are orbiting. The numbers were staggering. The object at the center of our galaxy has a mass of about 4 million times that of our Sun, and all that mass is packed into a region so small it must be a supermassive black hole. There is simply no other known object that could be that massive and that compact without collapsing into a black hole. We can't see the black hole itself, of course, because it emits no light, but we can see its profound effect on everything around it. It's like watching leaves swirl in a circle. You might not see the wind, but you know it's there. But the Milky Way isn't special. When we turn our telescopes to other galaxies, we see the same story playing out, often on an even grander scale. Take the galaxy Messier 87, or M87. It's a giant elliptical galaxy about 55 million light-years away. In 2019, it became a celebrity in the world of astronomy. Why? Because it was the subject of the first ever direct image of a black hole. This monumental achievement was the work of the Event Horizon Telescope, or EHT. The EHT isn't a single telescope, but a global network of radio telescopes all working together. By combining their data, they effectively created a virtual telescope the size of the Earth. This incredible resolution allowed them to peer into the very heart of M87 and capture an image of the black hole's shadow. What we see in that famous fiery orange donut picture is not the black hole itself, but the superheated gas and dust swirling around it just before it crosses the event horizon, the point of no return. The dark circle in the middle is the black hole's shadow, the region where light can no longer escape. This image was a direct visual confirmation of what Einstein's theory of general relativity predicted a century ago. It was a perfect match. And the mass of M87's black hole, a jaw-dropping 6.5 billion solar masses. That's more than 1,000 times more massive than the one in our own galaxy. Seeing this shadow was like finding the ultimate cosmic footprint, undeniable proof that these giants exist. Another powerful line of evidence comes from phenomena known as active galactic nuclei, or AGN, and their even more brilliant cousins, quasars. Have you ever seen a picture of a galaxy with an incredibly bright, star-like point at its center? That's likely an AGN. These galactic cores can outshine all the billions of stars in their host galaxy combined. Quasars are the most luminous type of AGN, visible from across the universe. So, what could possibly generate that much energy? The answer, again, is a supermassive black hole. But it's not the black hole itself that's shining. Instead, it's the material falling into it. As vast clouds of gas and dust spiral towards the black hole, they form what's called an accretion disk. The friction and intense gravitational forces within this disk heat the material to millions of degrees, causing it to glow with unbelievable intensity across the entire electromagnetic spectrum, from radio waves to X-rays. This process is incredibly efficient at converting mass into energy, far more efficient than the nuclear fusion that powers stars. Only a supermassive black hole, feasting on the material around it, can provide the engine for such a dazzling cosmic lighthouse. When we analyze the light from these quasars, we can also see spectral lines that are massively redshifted, telling us they are incredibly far away. This means we're seeing them as they were billions of years ago when the universe was much younger. This tells us that supermassive black holes have been a fundamental part of galaxy evolution since the early days of the cosmos. And that brings us to the jets. Some of these feeding supermassive black holes don't just swallow matter, they also blast some of it back out into space in the form of enormous, powerful jets of plasma. These jets travel at nearly the speed of light and can extend for hundreds of thousands, sometimes millions of light years, far beyond the confines of the host galaxy itself. We can see these jets with radio telescopes. They look like colossal plumes erupting from the galaxy's center. The physics behind them is complex, involving tangled magnetic fields and the accretion disk. But the bottom line is that only the extreme gravity and rotational energy of a supermassive black hole can act as the central engine powerful enough to launch such titanic structures. When we see these jets, we are witnessing the immense power of a supermassive black hole in action, shaping and influencing its entire galactic neighborhood. So, we have the orbits of stars telling us about a huge invisible mass. We have a direct image of a black hole's shadow. We have the incredible brightness of quasars powered by feasting black holes. And we have the colossal jets they launch across galaxies. But there's one more, very new and exciting piece of the puzzle. Gravitational waves. You might have heard about LIGO and Virgo, the observatories that first detected gravitational waves from merging stellar mass black holes in 2015. These are ripples in the fabric of space-time itself, created by cataclysmic cosmic events. But supermassive black holes merging create gravitational waves of a much lower frequency, with wavelengths that are light years long. Detecting them requires a different kind of observatoria, galaxy-sized one. Scientists have been using pulsars, which are rapidly spinning neutron stars that emit beams of radio waves like a cosmic lighthouse, as a giant gravitational wave detector. This is called a pulsar timing array. By precisely timing the arrival of these pulses from dozens of pulsars scattered across our galaxy, they can look for tiny correlated changes caused by the stretching and squeezing of spacetime from a passing gravitational wave. And just recently, in 2023, collaborations around the world announced that they had found the first strong evidence of a background hum of these low-frequency gravitational waves permeating the universe. The most likely source of this cosmic hum is the combined chorus of countless pairs of supermassive black holes, slowly spiraling into each other and merging at the centers of colliding galaxies. It's the sound of the universe's largest structures coming together. And it's another resounding confirmation that supermassive black holes are not just real, but are actively shaping the cosmos through their epic collisions. So, why do massive black holes exist? The evidence is overwhelming and comes from a multitude of independent observations. We see their gravitational pull on stars, we've imaged their shadows, we've witnessed their incredible energy output in quasars, we track the gigantic jets they launch, and now, we are even beginning to hear the space-time ripples from their mergers. These cosmic titans aren't just a curiosity. They are a fundamental component of the universe. It seems that most, if not all, large galaxies have a supermassive black hole at their center. Their formation is still an active area of research, but we know they grow by consuming gas, dust, and stars, and by merging with other black holes. Their presence and activity influence how galaxies form and evolve, regulating star formation and shaping the very structure of the cosmos we see today. They are not just monsters lurking in the dark. They are cosmic architects, gravitational anchors, and the powerful engines at the heart of galaxies. They are a testament to the extreme and awe-inspiring nature of our universe. The next time you look up at the stars, remember that hidden in the center of our own galaxy, and in countless others, these massive black holes are silently, powerfully reigning. What an incredible universe we live in. What part of this cosmic mystery blows your mind the most? Let me know in the comments below. And if you enjoyed this journey to the edge of reality, please don't forget to like this video. Subscribe to the channel for more deep dives into space, and hit that notification bell so you're the first to know when we post a new video. Thanks for watching, and keep looking up.